My name is Jason Yellick, and I'd like to talk with you about the Hyperledger Fabric lifecycle today. In particular, the new distributed chain code lifecycle introduced in version 2.0 of Hyperledger Fabric. Today, we'll be starting by talking about an overview of the version 1.x lifecycle. So basically how chain code lifecycle has worked up until version 2.0. Then we'll do a similar discussion of the version 2 lifecycle, sort of a high level, including a workflow for that, and then some permutations around that workflow. Finally, we'll move on to details about the version 2 lifecycle, and then finally some other notes and considerations that you should keep in mind when dealing with the V2 lifecycle. So starting out with how chain code lifecycle worked in Fabric 1.x. This should be a pretty familiar picture. You have a couple organizations, their respective admins, and an ordering service. And we would like to get chain code installed and instantiated so that we can begin transacting on the blockchain. So step one, each org admin installs the chain code to one or more of their peers. Step two, one of the admins goes out and does a LSCC deploy or upgrade transaction to instantiate that chain code, gets the result, submits it to ordering, that commits it all of the peers, and now the chain code is up and running. It's basically a two-step process, which is nice because it's a small number of steps, but it has a lot of drawbacks. To begin with, installing a chain code sort of grants this unconditional agreement to run that chain code on any channel that your peer is joined to, whether or not you agree that that chain code should run on that channel, or whether you agree to the assorted parameters to that instantiation. So for instance, you might want a certain endorsement policy associated with that chain code. You might want to have control over when that chain code is upgraded and downgraded. And you might simply not want to execute that chain code. So that's sort of one of the first big problems. And this is where we talk about this sort of distributed chain code lifecycle, or sort of distributed governance, distributed agreement. Actually, what do we have another word we were using for that, Jay?
Again?
You had said in your invite, decentralized. Sorry, that was the word I was looking for. Okay. Sorry. So continuing. So when we say that the new life cycle is decentralized, that's what we're talking about. That it's not just one admin making the decisions. That that's a problem we had in the previous life cycle, and that's something the new life cycle is here to address. Now, the second problem, which is a little less obvious, is that the instantiation, i.e. that deploy or that upgrade transaction, that includes invoking a init of the deployed chain code. But if we look at our picture here, you can see that that transaction actually only executes on org1's peer. So even though we may have set an endorsement policy for this chain code, that initial invocation of a init doesn't respect that endorsement policy. And in a lot of ways that's fine because it's being invoked by a trusted user and some other things, but it's still an asymmetry, and it's something that we wanted to fix. And then finally, this is more of an operational one. If you've ever tried to operate a Fabric network and you've tried, onboarding new orgs and that sort of thing, what you'll quickly realize is that even though you don't want to change anything about the code of your chain code, any of the chain code logic, if you want to modify, say, the endorsement policy to include a new org, Well, you actually have to go through this whole process of installing the chain code and performing an upgrade across the network, which is really unnecessary and causes a lot of churn. That's a bit of a pain, operationally speaking. So these are sort of the three big problems that we encountered in the original chain code lifecycle, which sort of leads to the three principles for the new V2 decentralized lifecycle. So first one is that peers only participate in a chain code if the org admin explicitly agrees, yes, I like this configuration for the chain code. So until the org's admin agrees, that peer will not, endorse the definition, the instantiation, and further, it will not endorse any invocation of that chain code, including its init function. So this basically, if we go back to our previous slide, we said that the installing agrees to instantiate unconditionally. This fixes that problem. Secondly, no exceptions to endorsement policies. This corresponds to our second problem we enumerated, which is the chain code init should be subject to the same endorsement policy as the rest of the invocations. We enforce that chain code init abides by the endorsement policy of the as defined for the chain code, just like every other transaction. But secondly, and this one is a little more subtle, in the v1.x lifecycle, LSCC really didn't have an endorsement policy. So in the v2 distributed lifecycle, we also enforce that the lifecycle chain code itself is governed by an endorsement policy, and decisions are validated based on that endorsement policy. So finally, the third parameter, which comes back to our operational problems, is that you should be able to modify your chain code definition. You should be able to change the endorsement policy, add collections, etc., without requiring an upgrade of the code across the network. So those three things are sort of the guiding principles behind the design of the V2 decentralized lifecycle. And you'll be able to see that reflected in just a moment when we do an overview of how the decentralized lifecycle works. Now, before we go into the overview of how the lifecycle works, it's important to mention sort of an implementation detail. And that's that V2 lifecycle is very much powered by a new V2 concept, and that is organization implicit collections. Now, if you're at all familiar with private data collections from v1.2 or 3 onwards, you'll know that the basic idea is that it's a namespace that's reserved that only certain members can read. So in V2, we've sort of extended that concept, and you can now associate which members can write to that namespace. And there's the set of implicit collections, which are defined implicitly, i.e. they're there without you having to do anything to define them. And you get one implicit collection per organization in your channel, and only peers from that organization may write to it, and only peers from that organization may read from it. So this allows you to implement a lot of interesting things in your chain code that weren't previously possible, notably things like voting schemes and ways for a chain code of one org to make a different decision than a chain code of another. That's a bit of a side note, and I don't want to get too off topic here, but implicit collections are sort of the underpinning technology behind the new V2 lifecycle, and you can use this in your own chain codes as well. So back to that overview. Just like with the v1.x lifecycle and the v2 lifecycle, the first thing we do is an install. Now the packaging format has been changed. There are some different things about the install, but conceptually, it's still just an install. You're putting the chain codes code package onto the file system, and that takes place as your first step, performed by each admin respectively. Now, secondly, and this is where things start to differ a little bit, org1's admin, in this case, is going to execute an approve for my org function against his peer, send that to ordering, and it commits. Now, this is modifying the implicit collection for org1, indicating that org1 agrees with this particular chain code definition that org1's admin is approving. Now, org2's admin is going to do the very same thing. Sends to his own peer, his approval, submits that to ordering, it commits. And now we have an entry in the implicit collection for each org indicating agreement to some chain code definition. At this point, org1's admin, or it could be org2's, but we'll use org1's in this case, invokes the lifecycle chain code on one of his peers and one of org2's peers, saying, let's go ahead and commit this definition, submits that to the ordering service, it commits in the public namespace, and now the chain code is defined. The definition that was approved by the two org admins have committed, and the chain code is ready to execute. At this point, typically the same user who did the commit of the definition would be the one who invokes init, and init can, execute just like any other chain code invocation. The peer will track whether or not init has been called and enforce that it's the first function called. But I think as people get used to this new decentralized lifecycle, you'll realize more and more that init usually isn't necessary. And it's actually a whole lot easier and more flexible to implement init logic inside the chain code itself if needed. A couple examples for this could be, first off, if you implement init inside a chain code, you can require each org to perform some action before the chain code is initialized. Or if you're doing something like upgrading your key schema, you can require a series of transactions that modify your database layout before you allow normal transactions to begin, because a single transaction would be too large. And really, to implement init logic, it's really very simple. You just pick a reserved key, perform a read against that key, and see whether it says the chain code has been initialized or not. If it's not, enforce init. Otherwise, allow things through as usual. And in fact, that's all Fabric does for you when in your definition you require init. So with the new lifecycle, not only are the semantics a little different, we had to pick a new name for lifecycle. Now, if you're familiar with operating a Fabric v1.x network, you'll know that lifecycle operations were done through a system chain code called LSCC. So LSCC is no longer the chain code used for lifecycle operations. Instead, there's a new system chain code called _lifecycle. And the underscore in the front is a prefix to indicate that it's a system namespace. The suffix of ending chain codes in SCC to indicate system namespaces was not one of the better ideas in Fabric v1.x. So underscore is now a reserved system namespace. _lifecycle is the lifecycle system chain code. And in Fabric v2, both the _lifecycle and the LSCC chain codes exist. Both are functional. And in the event that the distributed lifecycle has been enabled, first we'll check definitions done in the new lifecycle. And if there's nothing there, we fall back to the old lifecycle. But it is important to note that eventually Fabric will be removing support for the legacy LSCC. So it's a good idea to go ahead and migrate onto this new lifecycle as soon as possible, because at a later Fabric version, LSCC will be removed, and you'll be forced to move there eventually. So let's talk about how lifecycle works, sort of from a user perspective. Um, let's say you have three organizations, org1, org2, and org3, and everyone wants to run chaincode mycc. And we've agreed that 2 out of 3 orgs must agree that's the endorsement policy we want to go with. So what would this look like implemented? Well, someone's got to take the lead, right? So someone has to sort of administrate the process. And for here, we've chosen org1, but it could be really any admin. And what they would do is they would package this chain code using the pure CLI into what is now just a standard, tar-gz, and disseminate that package to the other orgs. Now, the other orgs, they can take a look at this package, and unlike in Fabric v1.x, where the package format was sort of a Fabric-specific thing, a CDS file, in the v2 lifecycle, these packages are standard tar-gzs. So an admin can simply use whatever commodity tooling they would like to take a look at that package, make sure it is, in fact, the chain code that they want to install. Now, everyone goes and installs this chain code package and commits that approval, sends that approved for my org transaction through according to the parameters that we sort of agreed out of band. So this is mycc, it's version 1, the endorsement policy is 2 out of 3, and so forth. Once everyone's done their approval, and again, typically we would wait for everyone, then the administrative org1 sends the transaction to commit the chain code definition for that channel, and the chain code is now operational. So let's look at this visually. We have 3 peers. The administrators install the chain code on each of those 3 peers. They approve the chain code with all of the same parameters. And then they commit that chain code definition. And now the chain code is defined. All 3 peers are ready to execute it. This is the standard workflow, and what you can expect to happen in most production Fabric networks. Everyone is in sync, everyone is in agreement, everyone does the same approval, and once everyone is ready, the definition commits. But we don't want to require unanimous agreement for everything. So here are some permutations. Let's say one of the admins doesn't install the chain code. One of the either they forget to, or they simply don't want to execute this chain code. Well, things still proceed just fine because all 3 orgs have agreed on this chain code definition, and that definition commits as normal. But only org1 and org2's peers will service invocations for that chain code, because of course the chain code is not installed on org3's peer. Hopefully that's unsurprising and what everyone would expect. Now the second one. Now this is sort of the crux of the difference between the v1.x and the decentralized lifecycle. And that's if org3's admin does not approve that definition. If org3's admin does nothing, well, it's still possible for the chain code to get defined on the channel because org1 and org2 agree, and we'll talk a little bit more about that later. But here the chain code gets defined, and even though org3's peer has the chain code installed, org3's peer will not execute that chain code. And that's because org3's admin never agreed to this particular definition. Well, what if they did agree that they wanted to run this chain code, but in a slightly different way? So in this case, you can see in bold here that for org3, their admin said, I want a policy of 3 out of 3 for the endorsement policy. All 3 orgs must execute. While org1 and org2 said, no, 2 out of 3 is just fine. Well, in this case, even though org3 has said, yes, I want to run this chain code, because org3's agreement doesn't match what's actually committed in the channel, org3 will still refuse to execute the chain code. So you get the same effect as if the org3's admin had done nothing. And so finally, this is sort of the worst case. Communications broke down. People couldn't agree on the parameters. Here we have org1's admin picked version 1.1. org3 picked a policy of 3 out of 3. We simply don't have enough agreement here on how this chain code should be instantiated. So in this case, the chain code could not be defined because we wouldn't be able to gather sufficient endorsements from the lifecycle chain code to actually get this definition committed. So I've been sort of avoiding the topic and alluding to it a little bit, but lifecycle is governed by endorsement policies. In the v1.x lifecycle, there were a few things going on. There were some sort of hard-coded validation rules, in the validation plugin logic, or VSCC as it used to be called, that treated lifecycle invocation specially. And the endorsement policy was also hard-coded there. And in the new lifecycle, everything is based off of endorsement policies. In particular, to commit a definition into the lifecycle chain code namespace, you need to satisfy the channel application lifecycle endorsement policy. So this is a channel configuration policy, much like the channel readers or channel writers policies. But this one defaults to requiring that a majority of the application orgs must endorse. So what this means is, in the default configuration, so long as a majority of the organizations in the network can agree on a change, then that change will be permitted. Now note, just like we saw back here, just because the network agrees on a definition doesn't force an org to participate in that chain code, but what it does do is it allows the network to make changes even if one of the actors is not participating. And so this could be maybe there's an urgent security bug or other reason that the chain code needs to change, and one of the organizations they can't be contacted, their administrators on vacation, something like that. We basically didn't want to default to requiring unanimous agreement, although of course this is a configurable policy in the channel config. So for those users who don't like the default of a majority, this can be modified to be, any policy that you like. In a more dictatorial network, you could require that a single specific org is the only org authorized to make, lifecycle changes. Now, secondly, there's another new endorsement policy, which is simply channel application endorsement. And this serves as the new default endorsement policy for chain codes when users fail to provide one. In v1.x, if you failed to provide an endorsement policy for your chain code, the default you got was any member of any org is an adequate endorsement, which makes for a very sort of convenient development default. It makes it very easy to get up and going. But we saw confusion from users who maybe they didn't understand what a or what an endorsement policy was, um, and they ended up with a default that didn't give them the security guarantees they were hoping for. So again, we think that this default of a majority of organizations must endorse, that's a pretty reasonable default, but it's just a channel policy. It can be changed to whatever the specifics that a channel requires. Now, here's another point that sort of was deliberately omitted in the previous slides. We talk a lot about these sort of sequences of events that org1's admin does something, and org2's admin does something, and the problem we always have when we have workflows like this is how do we know that what org1 agreed to is still valid and current. And so you can sort of think of a sequence number as being sort of like, an election year, or something like that. That, in sequence one, we're all voting on the definition, on the first definition of a chain code. For sequence two, we're talking about the first change to that definition. For sequence three, we're talking about the change to the changed definition, and so forth. And so what that allows us to do is we can approve a chain code and commit its definition at sequence one. And then while that chain code is operating, we can now begin approving a new definition at sequence two. And once the entire network has, agreed to that definition, installed that chain code, so on and so forth, then we can sort of atomically move up to sequence two. And then, the process repeats for sequence three, so on and so forth. So, this is just a new concept that you need to be aware of, that each incarnation of the chain code definition is assigned a sequence. And when we want to talk about this version or the next version, we talk relative to that sequence number. So let's go ahead and look at how this might, actually manifest. If we go back to our 3org example, if we have org1 and org2, they approve a chain code definition at sequence one. And because org3's administrator is on vacation, they go ahead and commit this chain code definition. And we end up back in that scenario where org1 and org2 will, endorse invocations of that chain code, but org3 will not. While org3's admin gets back from vacation, sees what the network did, says, "Oh, great, I agree." Now org3 can go ahead and approve the definition at sequence one, and org3's peers will now begin endorsing just like org1 and org2's. The important thing to note here is that without this sequence number, if org3 simply sent a new approval in, it would be unclear whether org3 was attempting to, approve the current definition, or whether org3 wanted to, maybe make some changes to the definition. And that's what we see in this next step here. Org1, org2, and org3, they want some sort of change, so they approve a new definition at sequence two. Once they've all approved at sequence two, we can commit, and that chain code definition now goes to sequence two. Of course, if you wanted to make another change to the chain code, you would make that change at sequence three, so on and so forth. Now, all of this has corresponding PRCLI commands, and they're not all listed here. In particular, there's a lot of query ability that you won't see here. But the big four you want to be aware of: there's a new packaging command, a pure lifecycle chain code package. That will generate that tar-gz we talked about earlier. There's an install command, which will take that package and install it to the peers. An approve command, which will approve a particular chain code definition for your org. Note that there is the sequence number attached to this, whether init is required, and so on and so forth. And then finally, a way to commit that chain code definition. So a few other notes and considerations. Um, One thing that is either a feature or a you know I won't say a bug, but a problem for operators that you may have run into is this notion of chain code fingerprint matching. If you've ever tried to package the same chain code multiple times um, and install it on different peers, what you'll often find in your logs is this chain code fingerprint mismatch error. And essentially, this comes down to the fact that even if you have the same set of files, um, getting them to package into exactly the same set of bytes is a little tricky. That you have things like file timestamps, you have execute bits, you have different file systems that support different attributes, and so on and so forth. So, in particular, if you tried to package a chain code with the Node SDK, and then you tried to package that same chain code with the Peer CLI, um, you would basically end up with different package fingerprints, and at your execution time, you would encounter this mismatch, which is not something that you wanted. Your chain code would otherwise execute just fine, but you would have these fingerprint mismatches that prevented things from working. So that exists no more. That's gone, which means actually that your chain codes can even differ slightly from peer to peer. That if org1 installs a chain code package and org2 installs a chain code package, those can actually be different chain codes. Now, they must implement the same logic, and by and large, we would usually expect them to be the same chain code. Um, but going back to one of our examples from earlier, let's say that there's a bug in the chain code that um, you know the chain code forgot to check if the third argument was nil um, before dereferencing it. So if someone sends in bad input, it can crash the chain code. Well, this doesn't actually have any impact on the chain code's read write set. It just causes the chain code to crash sometimes. So it would be perfectly possible for org1 to recognize this bug, fix it, and push a patched version of the chain code to their peers. And instantly, this chain code will no longer crash on their peers on this bad input. Now, org2, they get the email from org1 saying, there's this bug and we need to fix it. Here's my patch. They can take a look at that patch. They can evaluate it. In this case, it should be, an obvious. We'll accept it. But basically, organizations can roll out minor fixes to the chain codes independently of each other, and we no longer require that coordination. Of course, if you wanted to change the DB layout or what keys functions are accessing, we still have those same chain code execution guarantees via the endorsement policy um, that basically checks to make sure that the chain codes read exactly the same thing at the same versions and wrote the same things at the same versions. But slight variations in chain code logic, in particular around things like error checking, that's something that can differ. Um, Secondly, using the new lifecycle, you must enable the V2 application capability before any of these lifecycle commands will work. And this is a bit of a double-edged sword. When you flip that application capability on, the old lifecycle, the old LSCC namespace, becomes read-only. So essentially, if you are using the new lifecycle, um, all of your old chain codes continue working until they've been redefined in the new lifecycle. But basically you can't change them anymore. So if you needed to, for some emergency reason, go in and upgrade your version of the chain code, you would need to do that in the new lifecycle, not in the old lifecycle. It shouldn't be a problem operationally, but it's just something to be aware of. Make sure that you've thoroughly tested and and you're ready to migrate your chain codes as soon as the application capability is enabled. You should be able to do this essentially without downtime, because the old chain codes do continue to work. But once this capability is on, the old lifecycle is no longer an option for modifications. And finally, just in case anyone's immediate thought was, oh, let's turn off the capability to get the old lifecycle writable again. That might work, but like all capabilities, once you disable or once you enable a capability, disabling it is not supported. It's simply nothing that's tested, and things could go wrong in odd ways. So even if it might work, this is not a supported configuration, and there are lots of good reasons for this. In particular, once you've upgraded or once you've enabled a channel capability, that's part of the blockchain, which means other peers need to parse this capability. So there's really no going back. We have an immutable ledger, and if you were to disable the capability, it's still enabled in that section of the blockchain. So we really don't want to deal with disabling capabilities. And that's it. So hopefully this has been informative, and I'm always active out on the Hyperledger Rocket Chat, and yeah, thank you.
Great talk. Thanks, Jason. And there are several questions people might be interested in. As you mentioned, that it's currently possible to run different code for the same chain code across different organizations. And could you give some examples, like how that could be useful, some use cases or scenarios?
Sure. So, I touched a little bit on this, that, we now have these, for instance, org implicit collections. For those org implicit collections, the writes to them are only performed by my peers, right? I can execute a transaction only on my peers and write to this implicit collection. So I don't really need agreement from other organizations. Let's go ahead and say that I wanted to implement some sort of a bidding chain code. When my peer gets this invocation, my peer is going to write the bid into its implicit collection, but it wants to validate this bid according to rules that make sense for my organization. So maybe my chain code implements some proprietary logic, or maybe my chain code looks up, it makes an API call to a user database, basically something that's specific to my organization, to decide whether or not it's going to endorse or to enforce some validation on parameters. So that's really where different chain codes start to make sense, when different orgs require different logic, specifically around rights that aren't coordinated, things like implicit collections. Now, you can always do sort of additional validation and verification, things that, for instance, fail endorsement. Maybe in the official chain code, it allows arbitrary bids, but for you want to add some additional air checking, saying I will never endorse a bid for more than $100 million, or whatever the limit that makes sense for you is. So any sort of logic that's going to throw an error and prevent execution is also fair game for sort of a difference in a chain code. The things that you want to avoid are things that read from the state, or that write to the state, that other orgs are not going to implement. As I had mentioned, the The important thing is that the chain code must produce the same reads and the same writes across all orgs.
Okay. The third question is, do you have any tips or suggestions like people need to pay attention to while migrating to new lifecycle?
Um, sure. So the new life cycle is really meant to be very compatible with the old. The actual instantiation process is a little different, but none of this should require code changes inside your chain code itself. Um, However, as I had mentioned, I would encourage everyone to look at their chain codes and see, is a init actually being used to accomplish something useful? Um, could a init be removed from your chain code? And if so, during this chain code lifecycle migration, if you can drop the requirement for init, you will remove a step from your workflow, which is always a great thing. Otherwise, I think the sort of the big shocks are really the things that we set out to address. That you need to know the peer addresses of or the addresses of peers and other organizations in order to do your lifecycle operations. Um, you need to coordinate with the other administrators to perform their approvals. So there's more coordination, there's more knowledge, but that's really what was required to get us to this decentralized point. Um, so I guess if I could leave with a little bit of advice, it would be sort of to just um, take whatever coordination existed within your network before, around making decisions as to how and when to upgrade chain codes, and sort of just codify that into a sort of more formal procedure that um, you know uh, to explicitly enumerate, this will be the new endorsement policy, this will be the new version, this upgrade will or will not require init to be executed, and if you can sort of get this um, you know set of data that's required for this approved for my org command sort of um, you know down and sort of uh, if you can get this into a workflow as a concrete item, then this sort of approved step, the defined step, this should all just fall out very naturally from that.
Okay, thank you, Jason. Thank you for the great talk. We are now open for questions from audiences.